So we can go to now our next speaker, Timo. Are you there? Yes, great. So Timo is going to talk to us in the name of strong lens.
Sorry, I couldn't find my unmute. Okay.
Go ahead.
And now I cannot find my screen. Give me 1 second. Okay. Hi, everyone. So I'm Timo Anguita. I'm one of the chairs of the Strong Lensing Science Collaboration, and I'm representing the collaboration here. And I will tell you about our science cases, basically our strongly lensed transients or our follow-upable strongly lensed transients. So this is our typical introduction slide for the Strong Lensing Science Collaboration. At the moment, we are 3 chairs, but this is only a transition. Next month, it'll be 2 of us only. We have 61 members, and we span a very different range of sciences. So this is the only science collaboration that is a science collaboration of a method. So we have overlap with several other science collaborations, as we've heard. We've heard already from DESC, we've heard from AGN, we've heard from John in Milky Way, and we will hear probably in transients. Okay. So some of the science cases that we will deal with, several of them, most of them are static. And well, this is our typical list. We have a galaxy mass and substructure for 100,000 lenses. We will do cosmography with time delays. We will calibrate cluster max functions using strong and weak lensing. We will do quasar microlensing to understand the IMF of lensing galaxies, as well as the accretion disk structure of background AGN. Use lensing as a telescope and study the resolve properties of high redshift galaxies, and many more. But I want to draw your attention to the 2 of them that are transients, that are doing cosmography with time delays and accretion disk structure with AGN. And I will completely leave out galactic microlensing because I think it will be touched in the next talk on transients. So let me explain you briefly the 2 science cases. So time delay cosmography works in the following way. This is the typical strong lensing scenario where we have a background source. Let's say it's an AGN or a galaxy. The light rays emitted by the source are deflected by a massive lens. Let that be a massive galaxy or a cluster of galaxies, before arriving to the observer that sees multiple images of this background source around the lens. Now, let's imagine that our background source varies intrinsically, emits a burst of light, be it an AGN, it could be a supernova on the source galaxy. So we have a certain emission. This certain emission travels through the line of sight, through the different paths that create the different images. Since the different paths have different lengths and different time dilations, they will arrive to the observer at different times. This is what we call a time delay. And this is something that we can measure. And why is this time delay interesting? So here you have an equation that you can derive from the simple lens equation, where we have that this time delay surface is basically the product of 2 components. This dark blue component that I have here, that is basically the location, the original location of the source, the images, and the lens potential. And this light blue component here, that is basically a ratio of the angular diameter distances to the lens source and from the observer. Okay. We can simplify this as I'm showing you here on the right. This time delay is equals to this time delay distance, that is this factor right here, multiplied by the constraints that we obtain from modeling the lens. It's very easy to see from this ratio of these angular diameter distances that it is inversely proportional to the Hubble constant. So when we measure the time delays, which we can by monitoring multiple images of a background source and then basically shifting these light curves to measure the time delay and do a detailed lens modeling, we can obtain this time delay distance and the Hubble constant. And here I'm showing you some results obtained with lens quasars that were used to measure the time delays, do detailed lens modeling, and we can obtain values of the Hubble constant with up to an accuracy of 5% per system. So you can already imagine how transformative LSST will be by producing light curves for thousands of systems. Now, this science, time delay science, can be split into 2+1 systems, and I will tell you now in a while why I say 2+1. But this depends on the intrinsic variable source. So historically, we have the AGN that vary their brightness intrinsically and that we have used for the past 20 years to measure time delays. But now we also have supernova. There have been a couple of strongly lensed supernova that can be used to measure time delays. So here I'm showing you these two cases, quasars on the left and supernova simulated strongly lensed supernova on the right. And I'm purposely showing you these three so that you can see the different timescales that time delays can have. Here we have a time delay that is of the order of 120 days. Here we have time delays that are of the order of hours to a day. And here we have time delays that are of the order of months, okay? So we have a large range of variation. And the +1 class is any other lens transient that we may or may not have considered. There could be, I don't know, a tidal disruption event on a strongly lensed source or a kilonova. All these things can also be used to measure time. And the second science case is quasar microlensing, okay? Very shortly, quasar microlensing happens when we have a strongly lensed quasar. We have the light emitted from this quasar split into multiple images that can be seen in the lens plane. If we focus our attention to one particular lensed image, the light rays that produce this lensed image can encounter the gravitational potential of individual stars in the lensing galaxy. These individual stars can produce a focus and defocus of the light of each individual image, producing brightness variation, so a transient phenomenon. The speed of this makes the variation of the order of weeks to years. And this phenomenon is fairly common in lens quasars. You can see it in almost all of them at different scales. Here I'm showing you basically the best laboratory for quasar microlensing, that is the Einstein cross, where you can see that all the uncorrelated variations in this light curve that is, I think it's about 10 years long, is due to microlensing. Why is microlensing interesting? Well, several things, but here I want to focus on the structure of the accretion disk, okay? Here I'm doing a simulation of microlensing light curves, so basically this focusing and defocusing by stars in the lensing galaxy of an accretion disk that has several different sizes of the accretion disk. And we can picture this as a thermal profile of the accretion disk, okay? The light curves that will be produced by microlensing are the ones shown right here. And you can see that they are quite different for the different sizes. Now, if we interpolate to the cadence that LSST will have, and this is whatever standard observing strategy of LSST, you can see that we lose some information, but we still have a lot of it. So LSST by itself will give a lot of information on quasar microlensing. But I want to draw your attention to the right side, to the right plot, where we have a much more detailed accretion disk model. And in this case, it's a pretty simple one. In these high magnification regions, you can see these are scaled to match in the, okay, there's a scale to match in the magnification, but you can see that if we take a Schwarzschild black hole, for example, or a maximal Kerr black hole, in the high magnification region, they will differ only slightly. Okay, so this kind of high magnification microlensing events we would like to follow. It's one of the only ways to measure the detailed structure of high redshift accretion. So let's go back to the timescales so that we understand the follow-up ability of these events. Time delays goes from hours to a year, depending on the path difference. The intrinsic variability for time delay cosmology, we have AGN, that these are damp random walk type, so it can be from minutes to years. And supernova, as you all know, are a couple of months, a month to a couple of months, but it has a fast rise. Quasar microlensing has timescales of weeks to months. If we take into account all of this, plus the fact that all of these events have a color dependence, LSST cadence by itself will not be enough. There are several of these events that we will need to follow up, and thus we will need to trigger. Will this trigger be able to be done by a broker? And here are where the concerns in strong lensing come. We are very concerned on the performance of the different image analysis on lenses. These are very complicated sources to obtain photometry because they are blended, a lot of it. So in general, we want access to the pixels to understand what's going on. So the alerts may require multi-band comparison between different lens images shifted by the time delay. So for example, in microlensing, to issue a trigger for microlensing, we need to compare the brightness fluctuation between different images, and these need to be shifted by the time delay. That leads us to our third concern, that is the limited backlog for alerts. I understand it will be 30 days, But AGN variability and microlensing can have years variability that we need to compare between the different images. Additionally, there's a limited cutout size that it is my understanding that is about 6 arc seconds. 6 arc seconds might be just enough for galaxy scale lenses, but group or cluster scale lenses would not have this information. I'm finishing in 1 second. Even if we have this information, we will, even if we have the cutouts, we will need a detailed PSF information. We actually need to go to the pixels to assess the nature of the events that we're looking at. So we have already proposed a solution that is to run a reduction pipeline on known lenses. So the nice thing about strong lenses is that we will know all of them. We will know where they are. So there are no surprises on the alerts. These are not locations that we don't know. At least on the second year, we will know where most lenses are located. So we can have our own reduction pipeline with varying cutout sizes working on this library of coordinates. So I don't know if brokers can do this or if we want to do this by ourselves. And I'll leave the summary slide right there in case we have questions or discussion.
Thank you very much. We have 1 minute for a quick question. Do we have questions?
There are no questions yet.
Okay, good. So thank you a lot, Timo, for the presentation.